Warning, warning, all you potential pilots, pay close attention or your flight could end like this.
Hi, we're the Mayday team. John,
Peadar,
Jack.
we are here to ensure your plane doesn't fall out of the sky.
So what do we need to know then? Well, there are many factors determining a safe flight, but we're going to focus on drag. Drag is the force that resists the movement of an aircraft through the air, and it can be split up into two parts: parasite drag and induced drag. That sounds complicated.
We believe the key to understanding drag is the ability to visualise airflow in its different states. So we've been busy over the last 4 months designing and building a wind hull. Couldn't you buy one? I did like this one in IT Carlow, but it was 25,000, so I stuck to my straws and cardboard and remote control plane. Parasite drag is created as a result of an object moving through the air but is no way associated with the generation of lift. Parasite drag is made up of form drag, interference drag and skin friction drag. Parasite drag largely influences aircraft design, but it is important for a pilot to have a basic understanding of these forces.
Form drag is the drag created due to the shape of an object and the airflow around it. We ran 3 tests in our wind tunnel using smoke to visualise the airflow around different shapes. Airflow around the square resulted in the boundary layer separating from the object, which in turn leaves turbulent eddies in its wake. The airflow around the cylinder is similar but with less turbulent flow, and the boundary layer separation occurs at a later point on the object. Finally, the wing sections show laminar flow with no separation of the boundary layer. Why is this relevant to a pilot? Engineers study this to create the most efficient and aerodynamically designed planes. However, it is important for pilots to have a grasp of airplane design.
Interference drag occurs when airflow around one object interferes with airflow around another, such as with the fuselage and the wing. Eddy currents and air turbulence are generated. As you can see here with this plane, fairings are used to reduce interference drag.
Skin friction drag is the aerodynamic resistance due to the contact of moving air with the surface. Although this may only seem relevant to those deciding on the surface material of the plane, ice can form on the plane during flight, thereby increasing skin friction drag. Ice can have detrimental effects on a wing, as it can cause a wing to stall at a lower angle of attack. This is caused by the rough surface forcing the boundary layer to separate much earlier on. We ran 2 tests in our wind hull. The test results show a 12.5% increase in total drag on the airfoil, with the rough surface demonstrating the significance of this force. Induced drag is any drag that occurs because of the generation of lift. The air in which the airfoil is moving into is called the free stream. The airfoil directs this free stream downwards to generate lift. This is called downwash. Lift acts perpendicular to downwash. This means if we resolve the lift vector into its horizontal and vertical components, when the airfoil is at a positive angle of attack, some of the lift is opposing motion. This makes up a portion of induced drag. Wingtip vortices are another part of induced drag. From your study of lift, you know the wing creates a region of low pressure on top of the wing and high pressure below, as explained by Bernoulli's principle. The high pressure wants to get to the low pressure, so it tends to flow around the wingtip to try equalize the pressure difference. This results in the creation of a wingtip vortex. As the angle of attack increases on a wing, there is an enlargement of the induced drag force, and the lift force increases up to the critical angle of that wing. What is the critical angle? This is the angle of attack in which the airfoil becomes stalled. A wing is said to be stalled once its angle of attack is increased to a point where lift starts to decrease. In a stall, there is a large loss of lift and a massive increase in drag. We used our wind hull to visualise the separation of the boundary layer and to measure the increase of drag with the angle of attack. This is relevant to all pilots as the angle of attack is a variable you control in flight.
Wake turbulence is the disturbance in the atmosphere that forms behind an aircraft. This is made up of various components, however, the wingtip vortices are of most importance to a pilot to understand. Here is a clip of our RC plane played back at 25% speed. If you look closely at the ribbon on the wingtip, you will see a swirling action that is caused by wake turbulence. The wingtip vortices can take up to 3 minutes to dissipate. They sink at 150 to 270 meters per minute. The strength of these vortices is directly proportional to the weight of the aircraft and inversely proportional to the wingspan and speed of the aircraft. This means the strongest wake turbulences occur during landing, takeoff and climbing. It must be noted that helicopters create an incredibly strong wake turbulence. Here are a few clips from our interview with Mr. Peter Taus, a local motor glider pilot and instructor.
What are the dangers of wind turbines?
The wingtip vortex results in a vortex, a rolling motion. So the primary risk at low altitude is loss of control, and particularly an uncommanded roll.
We have now learned about drag and the dangers it can create for a pilot. Two core principles apply: precautions around wake turbines and the relationship between angle of attack, lift and drag, which in turn can create stalls.